This is Game AI Uncovered. My name is Paul Roberts, and in this video we're going to be looking at the A-star algorithm. Imagine you have a gridded environment filled with obstacles, and you want to get your agent from here to here. Well, there are many routes to achieve this, but which is the best? And how do we find the cells that make up that path? Well, that's what the A-star algorithm will do for us. Let's take a look at the flow of the algorithm. The first thing we do is add our starting position to the open list. Then we get into the main body of A-star. We search the open list for the cheapest node, and if this is a target, we can exit. But if it's not, we need to add its neighbours to the open list. To do this, we need to expand them, which is a little more complicated than this flowchart allows for, so let's swap it over for a minute. First, we determine if there are any more neighbours to explore. If so, we need to check if this neighbour is already on the open list or the closed list. If it's on either, we need to check if the new G cost, that's the cost from the start node to this position, is cheaper than the existing G cost. If it is, then we update the existing node's details and loop around to find the next neighbour. But if we jump back for a second, what do we do if the G cost was more expensive than the existing G cost? Well, in this case, we don't do anything, and we loop around to search for the next neighbour. Jumping back one more time, what happens if our neighbour is not on either of the lists? Well, in this scenario, we add the new neighbour to the open list before looping around to search for the next neighbour. When we run out of neighbours, we return to the previous flow where we move the current node, the one that we just expanded for neighbours, from the open list and onto the closed list. Then we loop around and search for the next cheapest node on the open list. I appreciate there was a lot of information there and a lot of new concepts, so let's explore some of those. First off, we have neighbours. These are simply the neighbouring cells on the grid. These can be in all 8 directions, or maybe just in the cardinal directions if that's what your game requires. Next up is the concept of lists. A-star has 2 of them, the open list and the closed list. The open list stores A-star nodes that we've come across in our search but have not yet expanded. The closed list is where A-star nodes are moved when they have been expanded, or in other words, we've added all their neighbours to the open list. But what exactly is an A-star node? Well, it consists of an ID, a G value, a H value, an F value, and a parent. The ID can be something as simple as the grid position. The G, H and F values are all costs. The G cost is the cost so far, and you can use the Euclidean distance to get an accurate distance. The H cost is the heuristic, or guess, as to how far away the target is. We can use something simple like the Manhattan distance for this. The F cost is the G cost and the H cost added together. This is a value that we will use to determine which is the cheapest node on the open list. And finally, we have the parent. This is just another node on the grid and is essentially a reminder of where we came from. So I mentioned heuristics there, so let's take a look at the 2 most common. The Manhattan distance is a really simple way of estimating how far away something is within a gridded environment. If we want to get from here to here, then using the Manhattan distance, we need to calculate how many steps are required across the horizontal axis and the vertical axis. As you can see, there are 17 steps on the horizontal axis and 9 on the vertical axis. If we add these together, we get the Manhattan distance. Next up, we have the Euclidean distance, which is pretty much just calculating the hypotenuse of a triangle using Pythagoras' theorem. That is, the square root of x squared plus y squared. Well, for this problem, we know there are 17 steps on the horizontal axis, so this is our x value. And we know there are 9 steps on the vertical axis, and this is our y value. Plugging these into our formula, you can see that 17 multiplied by 17 becomes 289, and 9 multiplied by 9 becomes 81. Add these together and you get 370. The square root of 370 is 19.23, which is the length of the hypotenuse, or the Euclidean distance. Finally, let's take a look at an actual A-star node. We're going to look at this green node here. The ID is a grid position, and our grid will be an array. So our position is 1 row down and 5 rows across. Remember, we start from 0, so it's actually the 2nd row down and the 6th row across. Next, we're going to jump to the parent, because we need that to calculate some of the costs. Our parent is a cell above to the left. That's 0 rows and 4 columns. So let's add this to the node. The parent is also important for putting together the final path at the end, and allows us to know where each node came from. Right, with the parent sorted, we can calculate the g-cost. Using the Euclidean distance from the parent, we moved 1 cell on the horizontal, so that's our x value, and we moved 1 cell on the vertical, so that's our y value. The square root of 2 is 1.41. But we're not done here. We also need to incorporate the g-cost of our parent. And this has a g-cost of 4, giving us an overall g-cost of 5.41 for this node. Next up is the heuristic value, and for this we're going to use the Manhattan distance. So with 12 steps on the horizontal axis and 8 on the vertical, we have a Manhattan distance of 20. The last value is the f cost. This is simple. We just add the g cost and the h cost together, and we're done. Okay, so now that we have all that covered, let's look at a search example. We need an environment with some obstacles, an open list and a closed list. We also need the start position of the search, which we are going to call A, and the target position, which we're going to call Z. And of course, we need an agent that's going to follow our path. So first off, let's create our start node. We know its ID. Its g cost is 0 because this is where we start, and it costs us nothing to get here. The h cost uses the Manhattan distance, which has 9 steps on the horizontal axis and no steps on the vertical axis, giving us a value of 9. The f cost is the g and the h added together, so this is also 9. And we have no parent, so this is set to null. This is important because when we reach the target node, we will be using the parents to work back to the start. When we hit a null parent node, we know that we have reached the start. Cool, let's put this on the open list and start the algorithm proper. Let's move our agent for now, so we have a better view of the environment, and then select the cheapest node on the open list. As there is only one node, we just take that. Node A has 3 neighbours to expand. Node B has a g cost of 1 from node A, a h cost of 10, and an f cost of 11. We also set its parent to be node A. This gets added to the open list. Node C has a g cost of 1.41 from node A. Remember that a diagonal move costs the square root of 2. It has a h cost of 9, giving it an f cost of 10.41. And we set the parent to node A. This gets added to the open list along with node B. The last node is node D, which has a g cost of 1 from node A, a h cost of 8, giving us an f cost of 9, and of course the parent node is A. This then joins the other nodes on the open list, and we have fully expanded node A so it can be moved to the closed list, and that is the end of our first loop around the A-star algorithm. To continue the search, we need to find the cheapest node on the open list. This means looking at f costs. As you can see, node D is the cheapest, so we can take that from our open list for expansion. Node D has 5 neighbours, some of which already exist. The first is node C, which is on the open list. We need to determine if it is cheaper to get to node C through node D than through its current parent. Well, the cost through node D is node D's g cost plus the Euclidean distance from node D to node C. As you can see, this results in a g cost of 2, which means it is more expensive to get to node C through node D than it is to get to node C from node A, so we can ignore this neighbour. Node E is new, so we need to set its values and add it to the open list. Node F is also new, so we repeat the process and add that to the open list. The next neighbour is node A, which resides on the closed list. Again, we need to check if it is cheaper for us to get to node A through node D. Obviously, this is never going to be the case. It can never be cheaper to go back on yourself. So ultimately, this neighbour gets ignored and we move on to the next. Node B already exists and is on the open list. Calculating the G cost through node D to node B is more expensive than going through its current parent, so we can ignore this neighbour. Node D has now been fully expanded, so we can move it across to the closed list. We haven't found the target yet, so we need to get the best option from the open list, which is node F. There are 5 neighbours from node F, the first of which is node E, which is already on the open list. Going to node E through node F is not a better route, so we ignore this neighbour. Next up are nodes G and H, which get added to the open list. The next neighbour is node D, which gets ignored as it costs more to go back on ourselves. Node C is also a bust, so we ignore that too. And with F fully expanded, we can put it on the closed list and find the cheapest node on the open list. Node H is the best option, so let's expand it. It has 5 neighbours and all of them result in us ignoring them. So we're just going to skip this node and drop it onto the closed list. Looking again at the open list for the cheapest node, this time we can see there are multiple nodes with the cheapest F cost. When this happens, just take the first one on the list, which gives us node G. This node has 8 neighbours, but to speed things up, I'm going to remove those that collide with obstacles and are not valid moves, along with those that are backward movements and ultimately get ignored. But remember, A* actually does these checks. We aren't to try and speed things up. So, from node G we have 2 nodes that get added to the open list. Node G is now fully expanded and can be added to the closed list. The 2 nodes on the open list we didn't choose last time are still there, so we take the first one of those, which is node E. Again, we will be ignoring uninteresting neighbours, giving us 2 neighbours to look at. The first is node I, which is already on the open list, and by calculating the cost to get to node I through node E, you can see that this is a better route than going through its current parent. So we update the existing node with the improvements. We have a new G cost, the heuristic won't change, but we have a new F cost and a new parent. The next neighbour is a new one, so we create node K and add it to the open list. Node E is now fully expanded, so let's add it to the closed list. We still haven't found the target, so we need to get the next best option from the open list. This gives us node C, which has 2 interesting neighbours. Node K is already on the open list, and it turns out that going through node C to get to it rather than going through node E is a better option, so we update its details. Next we have node Al, which is a new node, so we set its values and add it to the open list. Node C is now fully expanded, so it can be placed on the closed list. The cheapest node on the open list is now node B. There are 2 interesting neighbours connected to node B. First we have node Al, which already exists on the open list. It is cheaper to get to node Al through node B than through its parent node C, so we update Al's details. And then we have node K, which is already on the open list too. Going through node B has the same cost as going through node C. This is what is called symmetry in pathfinding, and we can just leave K as it is. That's it for node B, so it can be added to the closed list. Back on the open list, we find we have 2 nodes with the cheapest F cost, so we just take the first one we come across. We're kind of running out of space, which highlights one of the issues with A*. As the size of the lists increase, it means we have more nodes to search through, which can slow down the whole process. Anyway, node J is up next, which has 4 interesting neighbours. All of them are nodes that we haven't encountered before, so we add nodes M, N, O and P to the open list and move J to the closed list. The cheapest option on the open list is now node O, so let's expand it. Node O has 4 interesting neighbours. Node Q is new, so we set its values and add it to the open list, as is node R, node S and node T. With node O fully expanded, it can be moved to the closed list. Node S is now our cheapest option. This only has one interesting neighbour, which is node U. Remember, when we are skipping the exploration of neighbours, it's because I know they result in no change or are obstacles. The A* algorithm does not know this until it does the exploration, so it will not skip these. With node U added to the open list, node S can now be moved to the closed list. The cheapest option on the open list is the node we just added, node U. Node U has two interesting neighbours, both of which are new and get added to the open list. Node U can now be moved to the closed list. Node W is now the cheapest option. It has two interesting neighbours, both of which are new, so it can be added to the open list. Just note that the Z that's been on the environment the entire search is just to indicate the target position. It's not an A* node because we haven't created a Z node until now. With node W on the closed list, we find that node Z is the cheapest option on the open list. Node Z turns out to be the target, so we can stop processing the A* algorithm and use this node to calculate a path. So starting with node Z, we can locate its parent, node W. Node W leads to node U. Node U gives us node S. Node S leads to node O. Node O to node J. Node J to node G. Node G to node F. Node F to node D. And finally, node D leads to node A. With node A, we hit a null parent, which means we now have our path. Jumping back to the environment, let's take a look at this path. This has been Game AI Uncovered. Thanks for watching. Before we wrap things up, if you have an interest in AI, check out these books. Artificial Intelligence in Games will get you up and running with step-by-step code guides, and the Game AI Uncovered series is filled with insight from professionals about how they did the AI for the games that you love.